Google Earth Engine. So first of all, I will take you through Google Earth Engine, what it is, and why it is important to know about it, why you should care about uh, Earth Engine. So just like we have a supercomputer here, we have an HPC. Google has this machine called Earth Engine, where they it's like a community platform. It's a based on Google's cloud infrastructure to perform analysis, use whatever data you want. So and eventually the goal is to do high impact data driven science, and they have features like Google Earth Engine apps, they have Google Earth Engine APIs, they have Google Earth Engine datasets. So the first thing that you should see is the Google Earth Engine datasets. Now in the datasets, if you go to view all datasets, you can see that there are a variety of different datasets which are available here. So from the crop inventory in Canada uh, to this DEM dataset over Netherlands, and global map of oil palm plantations, uh, basic demographics. So this is a gridded world population dataset. Most important thing that you should care about is so these satellites like Landsat or Sentinel or even MODIS, it's difficult to analyze like traditionally. For example, if we talk about MODIS, right? So those of you who will be working in observations and even modeling, if you are making some analysis to construct a story for your research work, you'll need these data sets, right? Now if you download it from the USGS website, or you do in a traditional sense, every satellite data product, it comes with its own user manual. You have to follow the procedure to perform quality control. Some of the data sets are swath based data sets. So those, how many of you have heard about satellite swaths? So some of the data sets, for example, there is a TRMM 3826, I think, yeah. TRMM. Yeah, so there is this TRMM 3825 and 3826 products which are available. These are, I think, 1 hourly or 3 hourly precipitation. But the problem is that these datasets are not in regular gridded format. They come as these kind of swath datasets. Okay, so even if you grid them, it looks something like this. Okay, so it becomes challenging to do the pre-processing, and over such a large like you have to do it for the entire data. Google Earth Engine provides you an option wherein they have done all the pre-processing, they have done everything for you. You just have to fetch the data for your analysis. Just go here and just pick up the data and right away start doing your analysis. So this is for MODIS. They have for Sentinel, they have for the Landsat satellite. So in Landsat, there is Sentinel 1 mission, Sentinel 2, Sentinel 3, and Sentinel. So for the atmospheric chemistry community, Sentinel 5P is very important. So this was like brief about Google Earth Engine. Now, okay, these are the data sets. So Google Earth Engine has two APIs. Okay, one is a Python API, and the other is a JavaScript is a JavaScript API. So and also Google Earth Engine has got something known as the code editor. I'll just show you the code editor first. Maybe let's see. So code editor is if you just type. So first thing is you have to you have to apply for a Google Earth Engine account. Okay, you just click here, apply for Earth Engine, and let's say you go ahead, and you'll have to fill in some basic details and why you want an account on Earth Engine, and you submit this. So when I got an account that time, it was relatively easy. These days, I, I'm hearing that it's become slightly difficult, but if you give a good explanation and the people are still getting accounts. So the most direct way of working with Google Earth Engine is by using the code editor. Okay, so in code editor, if you see, let me just pull something from here. Okay, so if you just see the datasets catalog, and let's say we go to surface temperature, we go to, okay, and all the datasets are available. Okay, ERA5 reanalysis, NCEP reanalysis, NCEP, even CFS v2 hindcasts are updated at a like, so you can see CFS v2 hindcasts, they are available until 5th of June 2022. I don't know if any other place you will get this kind of an updated data set. So let us see the ERA5, and okay, so this is the page for ERA5 daily aggregates, and you can see here in the description, they provide a brief description of the data. They also provide a link of the original source from where the data is taken, and then in the bands, so they basically give you the information about the so what all variables are there in this particular data set, the units, the minimum value, maximum value, and also if it is being scaled by any number. Okay, and they also give you the resolution. So this data is at 27,830 meters resolution, so basically somewhere around 0.25 degree. So then you have image properties here, terms of use, citation. So this is the way you cite this data if you are using it. And they give this example script to load and visualize the data in JavaScript. Okay. So you just go to the code editor, paste this and run it here. So it is, you can see here, this is running. So it is first plotting daily total precipitation sum, then daily mean 2 meter dew point temperature. Yeah, so then it is plotting daily mean 10 meter U component of wind, and in the end, daily mean sea surface pressure. So you can, so there is also an option wherein what you can do is, so let us zoom over India. You can set the transparency so that the map is visible from the as the in the base, and these different visualizations. These are basically layers in this map. So what you can do is you can just select only one of them. Okay, so this is daily mean surface pressure. Now if you see this is daily mean 10 meter U component of wind. This is daily mean 2 meter air temperature, and this is for 15th of July 2019. So you can select the date here. You can, so this in this code, what they are basically doing is, so there is a data structure called image collection, which is a class inside the EE, that is the Earth Engine, And inside that, so there is a ECMWF folder. It has ERA5 and daily, and you have to select the mean 2-meter air temperature variable, and you filter July of 2017, like so 1st July 2017 to 31st July 2017, like filter start date to end date, and do this. So this is the ERA5 2-meter temperature to then precipitation, and this is the dew point temperature, mean sea level pressure, surface pressure, U wind. And this is the visualization. This is you define the palette and the minimum and the maximum. For the precipitation, this is for the 2-meter temperature. So you can see that the values are changing. So this is from 0 to 0.1. This is from 250 to 320 Kelvin. Now this is for wind. So this is from 0 to 30 meter per second. This is for pressure. So this is from 500 to 1150. So this is in hectopascals. And you see here this map dot add layer. So this you are plotting ERA5 TP, and you are selecting this particular date since it's a daily data. So in one day it has got only one map, and we use the corresponding visualization variable, and we give a name to this. So that is used as a layer here. So you can see here, we can turn this off. We can visualize the daily mean 2-meter dew point temperature. You can plot the daily mean, daily total precipitation. Okay. So you can just plot it, you can visualize it, you can save it. So this is the code editor. So you can just directly copy code from the datasets page of any data that you want from Earth Engine. Like even many of you might be using the TRMM 3V42 product. So even that is there. So you can see it's available from 1998 to 2019. So if you just copy this here and run it. So this will we are selecting the TRMM 3V42 product, and you can see this visualization for this. So it's a yeah not difficult to understand this visualization. You can give a proper palette here, and this will come as a nice visualization. So this is one. So this code is in. This is all JavaScript. Okay, and when Google Earth Engine came, mostly everything was people were using JavaScript. But then now it's Python API. It has it has evolved really nicely. So we will go through the Python API of Google Earth Engine and see what all you can do with the with Google Earth Engine. So this it can be found in this official tutorial at developers.google.com Earth Engine. So I'll just read this tutorial through, and it's an introduction to Earth Engine Python API. It says that within the last decade, large amount of geospatial data such as satellite data, the land surface temperature, vegetation, or the output of large-scale, even global models have become freely available from multiple national agencies and universities. These geospatial data are used every day by scientists and engineers of all fields to predict weather, prevent disasters, secure water supply, or study the consequences of climate change. When using these geospatial data, a few questions arise. So the first is, what data are available and where can it be found? How can we access the data? How can we manipulate these petabytes of data? Yeah, that's a big challenge, because not everybody has that kind of storage to basically get that much of data for their custom analysis. And in this tutorial, this is a tutorial to Google Earth Engine Python API. This is an introductory tutorial, and we'll see how to handle geospatial datasets with pandas and make some plots with matplotlib. Firstly, we'll see how to get the time series of a variable for a region of interest. The application of this procedure will be done to extract land surface temperature in an urban and rural area near the city of Lyon, France, to illustrate the heat island effect. Secondly, we will detail procedures for static mapping and exporting results as a GeoTIFF. So GeoTIFF is a data format. It's like we have NetCDF. So there is something known as GeoTIFF, and it is used widely by the remote sensing community, by people who use the satellite data sets. So it's important to also know about this GeoTIFF data format. And then there is another library known as Folium. So Folium is a mapping and visualization library. So this library enables the interactive visualization of the data on the maps. And so this they're saying that Folium library will be introduced to make interactive maps. And in this last part, we'll see how to include some Google Earth Engine datasets as tile layers of a Folium map. So exploring the Earth Engine data catalog, and so have you ever thought getting a meteorological dataset could be as easy as finding the next nearest area? So to convince you, visit the Earth Engine data catalog and explore datasets using the search bar. So let's say we need to know the elevation of a region, soil properties, and some meteorological observations. And the Earth Engine data catalog has everything. So you have the SRTM global elevation. So this is the NASA SRTM digital elevation at 30-meter global resolution, which is available. So let us plot this and see. So you can Yeah, so you can see that this is the elevation map of the NASA SRTM shuttle radar topography mission explained in this paper, Farr et al. 2007, and it's an international effort obtained digital elevation models on a near global scale, and this is provided by NASA JPL at a resolution of 1 arc second, which is approximately 30 meters. So, okay. And then there is open land map datasets with soil properties at resolution of 250 meters. So you can see this. This is the open land map clay content. So clay content at in percentage kilogram per kilogram at 6 standard depths at 250-meter resolution. And this is based on machine learning predictions from global compilation of soil profiles and samples. Processing steps are detailed in this GitLab repository. So yeah, you can go here and see this. Antarctica is excluded. And to access and visualize this outside the Earth Engine, so they also have a land GIS page on OpenGeoHub. So you can go here and visualize this data. Yeah, let's not go into too much detail. We can just plot this and see to get a feel of this data set. So you can see that this is the clay content in percentage kilogram by kilogram plotted globally. So yeah, this data set is available from 1950 to 2018. And then we have the GridMet dataset. So which is it is consisting of, it's a University of Idaho a gridded surface meteorological dataset. So it consists of the different bands, that is rainfall, maximum relative humidity, minimum relative humidity. The resolution is is 4638 meters. That is around 4 kilometers, right? So if we plot this, and this is from UC Merced, and only over contiguous United States from 1979. So if you have to use a global dataset, then I think ERA 5 will be the best available product. But if you are doing an analysis over the US, you can use the GridMet data from University of Idaho, and this is the maximum temperature plotted using this data set. Okay. And of course, the resolution, frequency, spatial and temporal extent, as well as the data source, example, the satellite image, interpolated station data or model output, vary from one data set to another. Therefore, read the description carefully and make sure you know what kind of data set you are selecting. Now to start with the Python API, so we will run this in Google Colab. To start with the Python API, the first commands that first of all you have to initialize the API. So you have to call, so you have to import the Earth Engine library. You have to say import EE, and then you have to say EE.authenticate and EE.initialize. So EE.authenticate, it will basically, what it will do is, so it will check whether you have an account for Google Earth Engine or not. We'll see that in a moment. Yeah. So you can see we are running EE.authenticate and EE.initialize. Now, this will basically, yeah, so this, it says that we got this link. We will get a code from here, generate token. Okay. Okay, so we got the token, and we have to paste this token here, and then we have to say e.initialize. So it says saved, successfully saved authorization token. So now you can use the Earth Engine library. Now you can do whatever you want. So the first thing is data structures in Earth Engine. So getting started with collections. So we'll talk about what are images, what is an image collection, feature. These are the different data structures of Earth Engine. And the syntax remains the same for JavaScript and Python API. Like you'll see very minimal differences in the syntax of Python and JavaScript API. So features are geometric objects with a list of properties. For example, a watershed with some properties such as name and area is an EE.feature. Images, which are like features but may include several bands. So for example, the ground elevation given by USGS is an image. And collection are groups of features or images. So for example, collection of images or collection of data set for, let's say, daily data for a month, it is a collection of the images at every day, right? And in the following sections, we work with the MODIS land cover, MODIS land surface temperature, and with the USGS ground elevation, which are EE.image collections. The dataset descriptions provide us with all the information we need to import and manipulate these datasets. The availability, the provider, the Earth Engine snippet, and the available bands associated with images in the collection. Now to import the land cover, land surface temperature, and elevation collections, we can copy and paste them in the Earth Engine snippets. So you can see here, this is the land cover variable. This is an image collection. We are loading the e.image, it's loading it from the e.image collection function. And this data mode is version 6 data, MCD12Q1. This will be loaded, the image collection will be loaded in this variable, and then we get the land surface temperature. So it's available from this MOD11A1. These are, by the way, official names of these products. So if you just search this variable, so you can see mod 11A1. This is MODIS Terra land surface temperature or emissivity daily level 3 global 1 kilometer sine grid product. So you can see the details about this product from here. And okay, so then you can then also import the also get the elevation data from the USGS data catalog or data collection, which is available on Earth Engine. And all of these images come in a different resolution. So let us run this example. Okay, we can read it here only. So all these images come in a different resolution, frequency, and possibly projection, ranging from daily images in a 1 kilometer resolution for land surface temperature, hence an EE.image collection with a collection of several EE.images, to a single image representing the data for the year 2000 in a 30-meter resolution for the ELV, that is the elevation. While we need to have an eye on the frequency, Google Earth Engine takes care of resolution and projection by resampling and reprojecting all the data. We are going to work on a common projection. So whatever you ask, so Google Earth Engine will reproject the data to that common projection, and you can define the resolution, which is known as scale. We'll see what is scale in Google Earth Engine, and whenever necessary, and of course have the option to force no reprojection. So as you can see in the description of the data sets, they include several sets of information stored in the several bands. So for example, these bands are associated with the LST collection. So band basically here means the variable. Okay. So the first band is LST day 1 kilometer. So which is daytime land surface temperature at 1 kilometer resolution. Day view time, which is the local time of day observation. LST night 1 kilometer, which is night time land surface temperature, etc. The description page of the collection tells us that the name of the band associated with the daytime LST is LST day 1 kilometer, which is in the units of Kelvin. And in addition, values ranging from 7500 to 65535 with a corrective scale of 0.02. So sometimes the values might be scaled with a particular scale. So for example, the land surface temperature values are scaled with 75.02. So if you multiply 7500 with 0.02, it comes to 150. So from 150 Kelvin to 65,535 into 0.02. So what you can do is you can filter so we loaded this LST, which is the land surface temperature, from MODIS, and you select so you select these variables, and we also need to select the bands we want to work with. Therefore we decide to focus on the daytime land surface temperature. So we select this band LST. So we select this band LST day 1 kilometer and its associated quality indicator QC day. So they also provide this quality. So some of the data sets might not also, like, they will provide you with the quality control parameter also, flag also. In this case it is QC day. So you can filter sorry, you can filter your dates from this I date to F date. So this is the starting date, this is the end date, and these two variables. So let us run this. And now we can either upload existing shape files or some points with longitude and latitude coordinates where we want to know more about land cover, land surface temperature, and elevation. For example, let's use 2 point locations. So the first one in the urban area of Lyon, France. The second one 30 kilometers away from the city center in a rural area. So we define a point. So for defining a point, the data structure in Earth Engine which is used is called geometry. So you have to say EE.geometry, and inside geometry there is point. So in the point you can define a particular latitude, longitude. So you have to first give the longitude and then you have to give the latitude. So we are saying, okay, we are saying, let's say the city center is an urban area, and we are saying, let's say the distance, like the something which is 30 kilometer away from the city center, it's a rural area. So we are defining urban point of interest and rural point of interest as the Earth Engine geometry point data structures, which we will use to extract the data over those locations. And so we can easily get information about a region or point of interest using the following methods. So the first is sample. So sample, it samples the image, and according to a given geometry and a scale of the projection to sample in, it returns an E.feature collection. First, it returns the first entry of the collection, get. So it which is it's used to select the appropriate band of your image or collection. Get info, it evaluates the server side expression graph and transfers the result to the client. So we are the client here, right? The server is Google Earth Engine. So if you want to get any information, you use get info, and other functions, they are used to do different operations on the server. So you have to think of it something like you are logging into your machine to Pratyush or Aditya using SSH. You are working there, but if you want something on your local machine, that is what get info will do for you. And then we can query the ground elevation and land surface temperature around a point of interest using the following commands. So please be careful when evaluating land surface temperature. According to the dataset description, the value should be corrected by a factor of 0.02 to get the units in Kelvin. And to get the mean multi-annual daytime land surface temperature, use mean collection reduction method on the LST EE.image collection. So you can see here, we select the scale, we say the scale is equal to 1000. So that is because I think this data set LST, or what is the resolution that it is available at? We'll just see that. Okay, you can see that it is available at 1000 meters global gridded resolution, and the two bands which are available are LST day kilometer and QC day. Okay, so we say that the scale is equal to 1000, and we basically want to print or get the information for the point, that urban point and the rural point that we had defined. So we had defined this U point of interest as the geometry point from Earth Engine, and we have already given the latitude longitude information here. So we just have to say elv.sample, and inside sample we give the first argument as the Earth Engine point of interest, and the second is scale. And then you have to say if you want to select the first entry of the collection, so the first function will do that for you. So you just say dot first, and then you say dot get elevation. So this elevation urban point, this is basically coming from ELV. So you can see we have defined ELV here. So get elevation and dot get info. Dot get info, it will return the in numerical form the data to us, so to the client. So similarly, we can calculate the land surface temperature and land cover type at this point. So let us see what it is. So the ground elevation at urban point, it is 196 meters. Average daytime land surface temperature at urban point is 23.12 degrees Celsius, and the land cover value at the urban point is 13. So these land cover value, the 13, it corresponds to an urban land, and you can run the above cells. So let us see this land cover variable. So mode is mcdq cd12 q1. Okay. So you can see here that we have this LC here, which is the land cover type. So we are selecting the LC type 1. So in the LC type 1, it is so in this it is from it's so this product is, it provides a global land cover types at yearly resolutions, yearly intervals. So which are derived from 6 different classification schemes. It is derived using supervised classifications of MODIS, Terra, and Aqua reflectance data. The supervised classifications then undergo additional post-processing that incorporate prior knowledge and ancillary information to further refine the specific classes. So you can see here that LC type 1, it is land cover type 1. It is from the annual International Geosphere Biosphere Program classification. So this classification type, so they have values from 1 to 17. So one is evergreen needle leaf forest. Two is evergreen broadleaf forest. So we got 13, right? So urban and built up lands, which is at least 30% impervious surface area, including building materials, asphalt, and vehicles. Okay. So then we have this as the cropland, the permanent snow, barren land, water bodies, cropland. Okay. So we get this as 13, and you can run the above cells with the rural point coordinates if you want to know a difference. So let us say if we run this with rural point coordinates, so we get this as 12. So 12 here corresponds to croplands. Okay. Okay. So yeah. Let us change this back to urban. Now get a time series. Now that you see we can get geospatial information about a place of interest pretty easily. You may want to inspect a time series, probably make some charts and calculate statistics about a place. Hence, we import the data at the given locations using get region method. So you can just say, so LST is your image collection. So you can see here is the image collection of consisting of the land surface temperature, MODIS land surface temperature collection, and you can just say dot get region and this U point of interest, and you can give dot scale and dot get info. And similarly for the rural area, you can do this. So this will, what this will do at a particular point. Now this data, you can see our date of interest are. So LST is defined as LST dot select. We are saying LST equal to LST dot select. This one dot filter date. So it is from 2017 January 1st January 2017 to 1st January 2020. So you can see here. So all the times, it will correspond. This will be a time series consisting of all the times for that urban area and for the rural area. So just printing out the first 5 values here. So you can see here it prints first thing as ID, longitude, latitude, time, LST, day 1 kilometer, QC day, and okay. So this is the first day, and this is the longitude, this is the latitude, this is the time, this is LST day 1 kilometer. So we are getting none here. Okay. And for this value, then for the fourth number, we are getting some value for this, which is 13808. So which is actually 13808 into 0.02 equal to 276 Kelvin. And we are also getting the last number. Okay. So none values appear in the LST. The associated quality indicator indicates a value 2, meaning that land surface temperature is not calculated because of cloud effects. We now define a function to transform this array into a pandas data frame, which is more convenient to manipulate. So we'll convert this into a pandas data frame. So what we would need an input as this Google Earth Engine uh, data structure, and we will output a pandas data frame. So you can see here that df equal to pd dot data frame arr, and we are having these headers. So header is equal to df dot ilog 0, df equal to pd dot data frame df dot values, and remove rows without data inside. So we will basically remove the rows with nan values and convert the data to numeric values. So this will do that. Convert the time field into a date time. Keep the columns of interest, and then you see yeah, and then you can see we can return a pandas data frame. We apply this function to get the two time series that we want. So one is the LST DF urban. So EEAR array to DF, and you pass in the first thing is this array, which is this one LSTUPOI, and then you give the list of bands. So the list of bands to basically extract, and then the temperature of mode is to Celsius. So you multiply with 0.02, which is the scale, subtract 273.15, you get the temperature in Celsius, and then so apply the function to get temperature in Celsius. So you just do to this column LST day 1 kilometer, you just apply this function and do the same for the rural points. So let us see what is the kind of data that we get. So you can see that this is the land surface temperature that we are getting. This is the time. This is the date time that we are getting. This is in pandas data frame. And now that we have our data in a good shape, so we can easily make plots and compare the trends. As the area of Lyon, France experiences semi-continental climate, we expect that land surface temperature has a seasonality influence, and the sinusoidal trend as described by Stallman 1965. So Stallman 1965, they expressed the land surface temperature uh, as a as a uh, as a dependent variable of time with this formula. So LST 0 represents the mean annual land surface temperature. Delta LST represents the amplitude between maximum and minimal land surface temperature. Tau represents the period of oscillation of land surface temperature, and phi represents an offset needed to adjust the time when LST t equal to LST 0. So consequently, on top of the data scatter plot, we plot the fitting curve. So you can just plot this fitting curve on top of the scatter plot that we got from our from the Google Earth Engine. So you can see here that this the gray one, the gray dots here correspond to the actual values. The and the this black one, so for the urban, and black one is the fitted plot. So you can see that it is matching quite nicely. And then you can get static plots of land surface temperature and ground elevation around the region of interest. we define this region of interest using a buffer zone of 1000 kilometers around Lyon, France. So you just say that upoi dot buffer 10 to the power 6. So 10 to the power 6 basically it works in SI units. So 1000 kilometers is 10 to the power 6. Also, we have to convert the LST EE.image collection into an EE.image. For example, by taking the mean value of each pixel over the period of interest, and we convert the value of pixels into Celsius. So you can see here that reduce the LST collection by mean. So you just take the mean of the collection here, and then you can just do a dot multiply. So this is a function of the Google Earth Engine, and dot add is also a function of Google Earth Engine. So you can either you can do this. Okay, so this was on pandas data frame, but if you directly want to apply these operations on the Google Earth Engine data, so data structure, you can use this dot multiply dot add operations. Then we use the get thumb URL method to get a URL, and we can use the IPython library to display the mean daytime LST map for the region of interest. Blue represents the coolest areas and red represents the warmest areas. So you can see that. So we create this URL styled image of a region around France, and then we plot this. Okay. So let us go forward. Yeah. So you can see that this has created this URL type image. So you can just, okay. So it is generated here also. So you can just like save this image as in the resolution that, like, save it as an image for your purposes, or for your analysis. So then the same we will have for the ground elevation. So this is the ground elevation map. And of course, you want to look at the closer regions on the map and clip an image by the region of interest. So we can clip it by the region of interest. So for example, we can say, so filter the feature collection to subset France. So we'll say countries dot. So we can get countries from E dot feature collections, and it is available from the FAO data collection in Google Earth Engine, and we'll say this. We'll select this band, and we will select France, and we'll clip by this region. So we just get the data for France. And we can also, so you can also export as a geotiff file. So after manipulating the Earth Engine dataset, you may need to export the results to resulting EE image to a geotiff. For example, to use it as an input of a numerical model outside Earth Engine, or to overlap it with personal georeference files in your favorite GIS. There are multiple ways to do that. Okay, so we explore two options. One is save the EE image to your Google Drive. Second is directly download the image. So this will save the EE image to your Google Drive. So you will just say task equal to e.batch.export.image.to drive, and it will save. So you have to give what image you want, the description, the scale, the region, and the file name prefix. The CRS is the coordinate reference system, and the file format. So we will see this, the link to download the geotiff. You can also do this. Like, you can just click here, and this should download your geotiff file. And then there is another library called Folium, which you can use to perform interactive mapping. So I will just run this here. you can see that you can generate this kind of an interactive map using Folium, on the base of which you can also have OpenStreetMap or Google Map to plot, to have plots uh, which look which look something like this. You can set the transparency so that the Google Map is visible below, and so this is how you can plot the elevation. So I think uh, we will